This video is all about arguing mathematically. Let's get straight into the examples. First of all, we need to show that this statement is false. When you halve a whole number that ends in 8, you always get a number that ends in 4. Before we show the statement is false, let's just think about what someone might do if they were trying to prove that it was true. They might try and find a load of examples and show that whenever you do have a whole number that ends in 8, you do get a number that ends in a 4. They could start off with an example. They could show that 8, when you halve it or divide by 2, gives you 4. So there's a number that ends in an 8, and when you halve it, you get a number that ends in a 4. And then they might try a number like 28. When you halve that, you get 14. So there's a number that ends in 8, and when you halve it, it ends in a 4. And they could do this with lots of numbers. For example, they could try 188. When you halve that, you get 94. So they can come up with as many examples as they like that when you halve a number that ends in an 8, you get a number that ends in a 4, like 14 or 94, for example. Hopefully you've spotted the flaw in this kind of argument. Just because it's true in loads of cases, it doesn't mean that it's always going to be true. You can find infinitely many numbers that end in 8, which when you halve them, give you a number that ends in a 4. Just because it's true for infinitely many, it doesn't mean that it's true for all of them. So that is the key thing to take away. To show that the statement is false then, all you have to do is find one example where this doesn't work, because the statement says you always get a number that ends in 4. So if you can find just one example where you don't get a 4, then you've done enough work. You don't need to do any more than that. So we could try 18. There's a number that ends in 8. When you halve 18, you get 9. And that clearly does not end in a 4. So that's enough work. All we've written in blue is enough to show that the statement is false. This example that we used to show that a statement is false has a name. It's called a counterexample. And we're going to look for counterexamples in the next two examples where we also have to show that the statements are false. Statement B says that prime numbers can't end in 9 because 9 itself is not a prime number. We need to show that that's false. So all we need to do is find a prime number that does end in 9, because that's the opposite of what it says here. So if we can find just one prime number that ends in a 9, then we have shown that the statement is false. So let's try numbers ending in 9. 9 is not a prime number, so that's not good enough. But the next number that ends in a 9 is 19. And that's the counterexample. We have found a number that is prime and it ends in 9. So just because 9 is not a prime number, it doesn't mean that you can't have a prime number that does end in 9. This isn't the only possible answer you could use. 29 also happens to work. 29 is a prime number, but it ends in 9. So that is just another counterexample you could have used. Just to be clear, I'm going to make a full sentence out of this. Moving on to statement C, it says the sum of 4 consecutive whole numbers is always a multiple of 5. We need to show that the statement is false. So again, all we need is a counterexample. Let's just take 4 consecutive numbers and see what happens. We could try 1, 2, 3 and 4. The sum of those numbers then is going to be 1 plus 2 plus 3 plus 4, and that equals 10. Now that happens to be a multiple of 5, so this is not a counterexample. This doesn't show the statement is false. If anything, this supports the statement. This makes you think that when you add up 4 numbers that are consecutive, you end up getting a number that is a multiple of 5. But just because it's true in this case, it doesn't mean it's always true. So let's try a different set of 4 consecutive numbers. How about 2 plus 3 plus 4 plus 5. When you add all of those together, you get 14. And this is a counterexample. So what have we shown? We've shown that 2, 3, 4, and 5 are 4 consecutive numbers whose sum is not a multiple of 5. Now, this statement here said that the sum of 4 consecutive numbers is always a multiple of 5. And when you've got a statement that says something like that, all you need to do is find one counterexample, because just one occasion where it's not true means that it's not always true. When it comes to showing a statement is false by providing a counterexample, you just need to take a bit of care. All of the statements we've looked at so far have said something along the lines of always. And when a statement says that, you just need to find one example where it's not true to stop it being true always. Now, not all statements will be phrased like that, and you need to take a bit of care. If this statement said the sum of 4 consecutive numbers is sometimes a multiple of 5, all you need to do is find one example where it is true. And this first example here would be an example where it is true. So it's just something to be aware of. Looking at statement D now, it says there are no multiples of 9 that are also prime numbers. Now, we have to show this statement is true. So this statement is true. How do we go about showing it? First, I'm going to show you the way not to do it, and then I'll show you a good way of answering this question. So here's a really bad way of going about it. You start off by listing the multiples of 9, like 9, 18, 27. Remember, the multiples of 9 are just the numbers in the 9 times table. And we're trying to show that none of them can be prime numbers. And remember what a prime number is. A prime number has exactly 2 factors. And what we've done in this bad answer is show that the first few multiples of 9 have more than 2 factors. So they are not prime. And just because it's true for all of these, it doesn't mean that it's always going to be true. The way to actually go about this question is to find a convincing reason why any number in the 9 times table can't also be prime. One way we could go about answering this question in a convincing manner is to show that every single number in the 9 times table is going to have more than 2 factors. Just like any integer greater than 1, all of the numbers in the 9 times table have got 2 obvious factors. They're going to have themselves as a factor and 1. 18 is going to have itself as a factor and 1. 27 is going to have itself as a factor and 1. And that's going to be true for every single multiple of 9. They are also going to have another guaranteed factor, and that is 3. And we know this because 3 goes into 9, so any number in the 9 times table is also in the 3 times table. So all the numbers in the 9 times table are guaranteed to have at least 3 factors. I don't need to know what the factors are. I don't need to know exactly how many there are for any larger numbers. I've done enough to prove that they've all got at least 3 factors, and therefore they can't be prime, because a prime number had to have exactly 2 factors. Let's explain that, writing as clearly as we can. We can say each multiple of 9 has at least 3 factors. It's going to have 1, it's going to have the number itself, which in this case is a multiple, and 3. And we can just give the reason for that in brackets. So, we've just said each multiple of 9 has at least 3 factors. A prime number can only have exactly 2 factors, therefore we can finish off with the following. There are no multiples of 9 that are also prime numbers. That's what we had to explain.